Hi everybody, we have Isaac here from Coda, and he'll tell us more about how to succinctly validate the chain. Introduce yourself a little bit, and then we can dive in.
Sure. Yeah, I don't know. Okay, so I'm Isaac. I work on a project called Coda. I guess the cool thing about it is existing blockchains. It's pretty much impossible for most devices to actually verify the chain because the amount of data that you need to verify is proportional to like the number of transactions which happen on the chain. In Coda, somehow we use snarks to kind of compress the whole blockchain down to one little proof, so any device basically can verify super easily by just downloading this one proof.
Cool. So let's get a quick overview of how that all works.
Sure. So I can maybe I can start by kind of explaining it at a high level, and then we can dig into any particular details. So I guess if you can imagine sort of a blockchain, it looks like this. There's some blocks. They go forever. In order to verify the chain, you sort of, you go down, you look at this block, you say, okay, is it good? Does it match, up with the previous state and so on? Oh, look at this block. Oh, is it good? Does it match up with the previous state and so on? And, you march down that way. So as I kind of alluded to, this is pretty crappy because it means if you want to verify the chain, like you need to look at all the blocks, right? Okay. So for example, if you're like on a phone or something, that's a no-go. So like what people do in practice is like you basically look at a third-party server and just look at whatever they say the blockchain hash is, like on MetaMask or something like that. So right. Okay. So what snarks let you do? Okay. So should I explain what's the deal with snarks? Or
High level, yeah.
Okay. So snarks. So basically, the idea is right. Okay. So you do some computation. Let me try and give a
Succinct example.
Yeah. So okay. So like imagine there's like oh crap. Okay. So I should have done this beforehand. Okay. So imagine you like run your you have some computer. It's like a big powerful computer. This is a computer, and it runs for like 1,000 years. So time goes by 1,000 years. Okay. So at the end, you're going to get some output. It says like the answer, I don't know, equals
42.
3. Huh?
42.
I don't know what you're talking about. So it says like the answer, for example, equals 3, and you say, okay, well that's all well and good, but how am I supposed to believe you that the answer equals 3? That's not my computer. I didn't run that computer for 1,000 years. I don't know. So and imagine furthermore that doing this computation required computing on a lot of data. So data. Okay. So what snarks let you do is they allow you to create a very small amount of data. So you can think of it somehow, maybe. Sometimes I like to think about it like a snapshot, like a photograph, of this computation happening. Yeah. Okay. And it's like a Polaroid, and someone wrote 3 on the bottom. And you just send that to someone instead. And the cool thing is this is like a snark. So it's very small. So it's small. It's like concretely, it's like I don't know, kilobyte-ish. And it's easy to verify. Okay. So how easy? Like on the order of like tens of milliseconds. Okay. So pretty easy to verify. And this took 1,000 years, so not bad. So okay, so that's snarks. So cool. That's like general principle. Now how can we use this to solve our problem of like let's not have to download every transaction which ever happened to verify the blockchain. You do it in the following way. Basically. Let's see how to best explain it. Okay, so if you think about this, what it said is, any computation that you have, no matter how long it takes and how much data it operates on, you can make this little proof, which is small and easy to verify, which convinces someone that that you ran that computation and really the output was really, what it was supposed to be, what you claim it is.
But you also need to know input data.
Well, maybe. So you don't, right? So you don't need to know the input data.
It just says there's some input data.
It says there is some input data, so that if you were to run this program on that input data, this would be the output. Yeah, exactly. Thanks for clarifying. So, okay, so verifying a blockchain, that's an algorithm, that's a computation, which means we can use snarks to certify its execution. Now we need to be sort of careful about how exactly we do it, because if you do it in a naive way, it's not going to be efficient. It's not going to really be feasible. But snarks are still sort of cutting-edge technology. You need to make sure you treat them nicely. You can't throw anything at them. So let me kind of explain a little bit more in depth how it actually works. So, okay, so we have this idea that snarks can sort of this one. We have this idea that snarks can sort of certify some computation so that you can be convinced of the answer without having to redo it yourself. Okay, that's the idea. We need to keep this technology in our mind. Well, I guess can I use this? I guess I can use this. So this was a bad whiteboard work. So how do we use this for in the blockchain context? And by the way, like this technique that I'm about to now I'm looking at this.
No, you're.
Oh, I'm still looking at this.
This is
okay.
Overall, this is just focused on a whiteboard.
Oh, okay. So this technique that I'm about to describe, it has really nothing to do with I mean, it doesn't have anything in particular to do with blockchains. It's very generic, and any sort of state machine really, you can certify its execution in the way that we're going to describe using snarks, and blockchains are some kind of state machine. Yeah. So okay, so yeah. Okay, so how does it work? So. Well, yeah, in a blockchain, we have a state. Blockchain state. OK, and what's in the state? Well, OK, for example, let me talk about Coda. There's the Merkle root of the database of accounts. And there's some consensus-related information. Essentially, there's maybe a little bit more than this, but so this is essentially information that you need to make progress in consensus, to propose a new block, and also to do chain selection. So this has things in it like length, and then a bunch of more sort of Ouroboros-specific stuff. I'm always bad at spelling this. Ouroboros-specific stuff, which we can get into later if there's interest. OK. So.
But if it was proof of work, that, for example, could be the overall
yes,
complexity.
Exactly. If it was proof of work, this, for example, could be the strength of the chain, the expected number of hashes. Right. This would have like the expected number of hashes, that were needed to compute in this chain, the strength, and also the last few difficulties in block time, so that you could do difficulty adjustment. Mm-hmm. But don't use proof of work. It's bad. Seriously, like we're in a climate catastrophe. Oh. No. Okay. Everyone. Hopefully, everyone knows that by now. Turn off your Bitcoin miner. But so let's see. So
people just started turning them on.
Huh?
The electricity price going down.
Okay. Well, anyway. So right. Okay. So maybe I'll come back here. So we have this blockchain state. And then we sort of have like an update blockchain function, OK? Update function. OK? And basically, what does this do? So the input is, like the previous state. And say, a block, whatever that is. And the output, is the new state. OK? So what we want to do is basically make a snark which somehow says, I know some sequence of blocks, so that if you call this update function with that sequence of blocks on, starting on the genesis state, you'll end up in state S. Okay? And then, so yeah, we have some snark, which says, will be my diagram for snark. It's a photo. It says you can get from genesis to state S. And it says something about the update function and so on. Update, blah, blah, blah. So then, if I want to convince you, for example, oh yeah, here's how much money you have in the current blockchain, for example, or like I really sent this payment to you or whatever. I keep looking at the wrong camera. I just send you this proof. That convinces you, you see all the proofs floating out there on the network. You pick the strongest one. That convinces you about what the current state is, state S. Then you would know from that, you would know the Merkle root of the database of accounts. Then you have to get from somewhere, you would ask another node of the network for a Merkle path into your account. And then you see your balance, $17 or whatever, $42. Yeah, anyway. Yeah, so that's the basic idea. Okay, so now how do you actually do this snark? That's this technique of recursive composition, and I can explain that, or we can go on to something else.
No, I mean, this is...
That's the core, right?
Yeah, that's the core.
Okay. Yeah, we can talk about that. So,
I mean, I think like an interesting part here is that snarks itself, right, you can only apply it to a specific function, right? So like when you have this photo, you actually need to know kind of what computation was done ahead of time
Yes, that's right.
that food approves you.
Yeah. So snarks, like natively or whatever, only work with like fixed size computations. So, the naive thing would be you'd have to sort of say ahead of time, like yeah, this, but for 10 blocks or for 1,000 blocks. You'd have to fix the number, of blocks that you wanted to sort of compress into one snark. And so the technique of recursive composition makes it possible to not have to do that, to certify the execution of an unbounded number of iterations of this update function. This is a general technique. So first I'll talk about the general technique, which you can apply to any snark, and then I will talk about some snark-specific things that. So usually you wouldn't want to use this general technique because it's really slow. But then there's some kind of magic that is true about some snark constructions, which let you to make this technique much more efficient than you would naively expect. Okay? So let me explain first the general technique. It's a very interesting technique. Basically, it's the following. Let's see. What's the best way to explain it? Okay, so before we talked about this update function, maybe I'll still talk about it in those terms, even though it's really a bit more abstract. But let's say we have some function u, okay? And this is like our update function. Function u, from some state to some state, okay? Okay, and what we want to prove is basically let's say it like this. So okay, maybe I can say this about snarks. With snarks, there's always this sort of public thing that's like what I wrote on the bottom of the Polaroid. That's, you call it like the instance or the public input maybe. So whenever you want to like define a snark, a specific snark construction, you say, okay, what is the input? What is the instance? And what is the and what are you proving about the instance? Okay. So here's what we want to do. We'll have our input, or our instance will be a state. Okay. Yeah, maybe two states. S0 and S1. Okay, and we'll prove Okay, I'm not going to explain it in full generality because it doesn't matter for the main idea. Okay. So we want to prove basically. Okay, instance this. Yes, there exists some number n. Maybe I won't use that. I don't know who's watching, but let me try not to use any mathematical notation that I don't need to. There is some n, some number n, so that if you do u n times, on S0, it's equal to S1. Okay, just abstractly. Really, you'd want to, if you want to talk in full generality, then there's also some sort of input or whatever, like the blocks, the transitions, the state transitions. But let's think about this trivial case because it still illustrates the general concept without having to write more notation. So, so it's clear what we would like to do. We would like to have a snark which lets us prove statements of this form. Okay. So how are we going to do it? Okay. Here's the idea. Yes. So instead, this is one thing, but instead, how about we do this? Instead, prove S0 is equal to S1, or there is a proof, a snark, pi, so that pi proves, oh, sorry, there's a proof pi. Okay, so either S0 is equal to S1, or there is a proof pi and a state S, so that pi proves the statement S0 S, and U of S is equal to S1. Okay, so will you ask me some questions so that to clarify what I said?
Yeah, I mean, pretty much, yeah. It's you define a recursive function, right, where you have the base condition and then a step decomposing it into.
Right. Yeah, it's like induction.
Yeah, it's induction step.
So you want to prove that if you do this some number of times, you can get from S0 to S1. What you prove is either, oh, you're already there, S0 is equal to S1, or somehow, I already know that I can get from S0 to S some intermediate state, and if I can just take one step from S, I get to S1.
And you don't care. You just care that the proof exists. You don't really care what that proof is.
Yeah, it doesn't matter what it is.
It's not an input. Yeah.
Yes, it's part of the witness. And so the tricky part here is what is meant by pi proves S0, S1, right? I mean, what does that mean? Well, it means if you run the snark verifier on pi with inputs S0 and S, you'll get true, right? Mm-hmm. So we need to make this more explicit so that,
Snark verify.
Yes, snark verify on pi with S0 and S equals true. But even this is not enough because snark verify, it doesn't just take the proof and the instance, it also takes another argument, which is called the verification key. Okay? Do you know what I'm talking about?
Is that the program itself, pretty much?
It's sort of the program itself, but yeah. So people might know, like with snarks, it doesn't make sense to just say snark verify. Let me say it like this: for any particular like program that you want to certify the execution of, you can generate parameters for that program. And probably many people know that there's this MPC that you have to do when you're using pairing-based snarks, which is like, to generate good randomness to use, right? And so that good randomness is for generating a proving key and a verification key. And that verification key, it's sort of like a description of the program. It's an additional input to the snark verify function. Does that make sense?
Yeah. So, I mean, that's what toxic waste pretty much is when they generate it.
Yeah. So So the toxic waste is like a byproduct of generating the verification. So So you have to pass in the VK. Okay. But which VK? This is a bit of a problem because it's supposed to be the verification key for the program that we're right now defining. Right? You see what I'm saying?
Yeah, so I mean, you're pretty much saying, so you have you from you, right? And you decompose this part out, and you're saying, hey, there is a pi without this part.
Yes.
But the pi itself proves this part, right?
Yeah.
So pretty much you need a VK that proves, I mean, depends on how pi is structured, right? That's what.
Right. So what I'm saying is, like, what we would want is that VK is the verification key corresponding to the statement that we're right now defining.
Yes.
Right?
Yeah.
So there's a chicken and egg problem.
To the step itself, pretty much. To the induction step, not the.
No, VK is not an induction step. VK is the full induction.
Yeah, to the whole statement that says either base case or you take one step.
Yeah.
Right? So that seems a bit problematic, right? Because, well, we didn't finish defining the program yet. How are we supposed to do a parameter generation and get the verification key? So, well, I don't know. How about we just make the verification key part of the input?
It's input, yeah.
So, right. So we just say snark verify on. Right. So this isn't. Yeah. Well, that's not going to quite work. Sorry. So okay. So sorry. Let's not make it part of the input yet. So somehow we're going to have to get this VK, right? So here's what you do. You say. Right. Yeah. I guess you could make it part of the input. So you can think it's like a binder, like in a programming language, right? Like it's not in scope. VK is not in scope.
Yeah.
So we need to bring it to scope somehow. In the snark, there's two ways that you can. I mean it literally. There's two ways that you can bring something into scope. One is you have it be part of the instance. Mm-hmm. Okay, that's this binds the variables S0 and S1 by declaring that they're part of the instance. Or you can do this You can do this non-deterministic choice. That's the other binder. So you can say there is a proof pi and a state S, and now I can talk about pi and S and what follows. Okay? Mm-hmm. So I can either bind it here or I can bind it in there is. The most obvious thing to try is to bind it here. So to say, okay, part of the instance is also VK, so when you verify the proof, you actually sort of pass in the verification key as part of the input. It's sort of like a function that calls a function. You can kind of think about it like you're passing in a function as an argument and it calls itself. It's like if anyone ever implemented like a fixed point function or something, or Y Combinator, It's kind of like that. So what?
Nothing.
Yeah. So yeah, okay, but actually, it's very interesting. You can't do this. Why can you not do this? This is a great trick. You can't do this because actually, the size of the verification key depends on the size of the instance. So let's say the instance has size. Let's say the instance would have to have some size. Let's say it has size k. All right, for example. Well, it can't actually have size k because if it has size k, then its verification key has size basically k plus 1. Mm-hmm. So
then your instance has 2k plus 1.
Yeah, for example, right, or k plus at least k plus 1. Yeah. So okay, so that's contradiction. So it can't have any size. So that doesn't make sense. So that's actually a no-go. Mm-hmm. So that's too bad, but it's kind of funny. Okay, so what's our only other choice? We only have one other binder. Oh, this marker died too. We only have one other binder. Which is there is. Okay, so that's where we need to bind it. So there is a proof pi and a state S and a verification key such that this. Okay, so now we've bound it, so that's good. Okay, so now we take a look at what we've done so far. Is this going to work? No, it's not. Why? Because we said it's just an arbitrary verification key. So that's totally useless.
It's going to always return true.
For example, it could
Well, you can always find such a key that it
yes,
returns
exactly.
true,
You can
yeah.
always find a key that returns true. So that's no good. So now we think, and now here's the amazing thing. Now we look back at our instance, and we say, OK, what was the problem? The problem was that in order for the verification key to have sort of a fixed size or whatever, like the instance needed to have a size that didn't depend on a verification key.
So do we hash the key and just pass the hash of the key?
Yes, exactly. So instead of having the instance be a pair S0 and S1, you can have it be just a single value, which is a hash. So it's just a hash h. And then what you do is you say, we use our other binder. So now S0 and S1 aren't in scope anymore, but that's OK, because we have this other binder, which is there is.
Yeah,
so
there's S1 and 0
yes, so we say there is S0, S1. Oh, I was using script S. S0, S1, VK, so that, first of all, this is the right S0, S1, and VK. So hash of S0, S1, VK is equal to H, and everything else that we said before. So,
But that doesn't work, right?
oh, why not?
Because you will naturally have to pass this hash in here, but S doesn't match, right?
Ah, OK. So here's what. So yes, right. That's a good point. So now we need to just change this. So instead of saying snark verify VK and this, we say snark verify VK with hash of S0, S, and VK. OK.
But also, are you implying that I can I snarkify snark verify function?
Yes.
So that's the whole point of recursive
Yeah,
snark.
so that's the point of recursive composition. So the snark verify function is defined regardless of what the verification key is. So and it's small. It's quite simple. So this is just some computation.
How many gates is that?
So which one do you use?
So you use like the Shannon, Dara's, Peterson hash function.
And so this, in practice, is this recursive snark applied to every block or to every transaction?
Yes, that's a good question. So what I described was talking about it for every block, but you need to do something with the transactions. And in particular, in order to decouple, it's important in Coda, for example, that the block time is short. This is important for Ouroboros. So you want to decouple the block time from the proving time as much as you can, and the snark proving time, because it's pretty long, right? So if all the transactions that you wanted to include in the block you had to do at the same time, as you produce the block, that would not be so good, because you could only do very few transactions in the short block time that you want to do. So in Coda, there's this kind of pipelining that goes on where there's really actually kind of a buffer of transactions which have yet to be snarked yet, but are also kind of part of the state. And when you win a block, you essentially enqueue things onto this buffer and also compress some things that have been compressed in the meantime from the beginning to clear more space. And yeah.
Oh, so every block contains some transactions yet to be snarkified.
Yes. As in addition to like some transactions that had been previously included that have now been snarkified, that you sort of pop off this queue.
But in reality, is it the case that you, like, let's say I have two transactions, right? TX1 and TX2.
Yeah.
Is it the case that I'm first going to prove that TX1 is valid?
Yeah.
And then I'm going to prove that I have the snark of TX1 and TX2 is valid, like recursively?
Yeah.
Or is it the case that I will prove TX1 separately, TX2 separately, txt3 separately,
Oh, yeah.
and then somehow aggregate
Merge
them.
them together. Yes, yes, yes. Actually, that's how you do it, and that's important because otherwise things are going to be really slow and you're going to have really crappy throughput, right? So.
But then it becomes interesting, right? Because
Well, you have state.
imagine that Ilya has 10 tokens,
Yeah.
and I have transaction txt1 which sends them to me, and transaction txt2 that sends them to you.
Yep.
Then you can naturally prove both of them. So the aggregation step is in a smart way, rules that out.
Let me explain. Yeah. So.
I mean, it proves them when you apply the state.
Yeah. So. Right. As you said, we have these transactions. Let's say there's 4.
Oh, I see.
Like you prove the state transition, not
Right. So
transaction
because
itself.
these are sitting in a buffer, they've been linearized. There is a definite order on them, and so we can do it without worrying about what you said basically.
I see. So effectively, there was like some state 0 here, state 1, state 2. Those can be computed very quickly compared to Snark computation, right?
Yes. Exactly. Yeah.
and
Right.
you store them with a buffer of transactions as
Yes.
well, right?
Yeah. Exactly. And then what you do is instead of here we had one call to Snark verify, but you can imagine having 2, and that's just what you do. So you have a proof that verifies 2 proofs, and so you sort of go up a tree. So right.
And it's also going to prove that the output state of one of the transactions equals to the input
Yes,
state.
exactly.
Yeah.
So it verifies 2 proofs, and it checks that they match up. So
And then it's like some logarithmic ascend.
yeah, right. So let's say you do 2 once. So right, so here it's like S0 to S1, S1 to S2. So you just like merge these together, and then you can get from S0 to S2. Similarly, you merge these together, and you can get from S2 to S4, and then you merge everything together. And so, right, and so like the total wall clock time taken to do this is logarithmic in the number of transactions instead of being linear in the number of transactions. So you're happy.
But you need number of workers, which is linear in number of
Which
transactions.
is linear in the number of transactions. Yeah. The total amount of work that you do is
And also, I mean, all the workers need to have pretty much a somewhat sophisticated data structure to contain the chunk, like just chopped up state.
Yes, yeah. There's some data structure which, if you go on GitHub and look at our code, it's in a file called parallel scan. I didn't name it. I don't love this name, but anyway, it's a tree that has all sort of the intermediate states of all these computations and holds on to all the data. It's sort of complicated, yeah.
What does ML stand for?
Oh, okay. It's OCaml.
As obvious from the abbreviation. Oh yeah, it actually has ML. Yeah. Okay.
It's a suffix, yeah.
It's because of it's a part of the ML family of languages, like SML. Anyway.
All right. So usually one snark, how long? Like for one state transition?
It's something like 30 seconds.
On a CPU, right?
On a CPU.
So on a GPU it will be faster. Matter Labs?
Yeah. So you have 30 seconds, right? And then you have a height of it.
But this is also 30 seconds? Because this is a different proof, right?
Roughly.
Okay.
It's
So they're all the same.
well, they're
Well, the different
it's
function.
same order of magnitude. Let's say, yeah.
So logarithmic transactions. So how many transactions do you have in the block?
I don't remember the exact number, but let's say you want to do like 1,000 transactions or something.
But transaction is final when it is included into the buffer, right?
Yes.
So we really don't care how long this takes.
In some sense, yeah.
Yeah, but that's your pretty much. How soon do you have a snark for this?
For the whole
Right. Yeah, let's say it's next day. Yeah, but then as a mobile phone, you're then loading the Snark 1 day worth of blocks, which is,
Yeah.
Which is still a lot.
It is. So
How often do you produce blocks? I mean, maybe that's like a good segue into
so we haven't went into consensus and stuff.
well into the chain itself. Yeah.
So we haven't totally set the parameters. Hopefully it will depend. We have to like get the proving time a little lower, but hopefully it'll be somewhere around 10 seconds for one block. That's the hope for the block time. It might be a bit more. I don't know. I don't want to commit. It's not on the board.
You don't want to commit.
you cannot erase things from blockchain.
There's already a ZK somewhere of this.
But also in practice, so once these proofs were proven for one block, right, and we're moving up the tree, are you already starting proving the lowest level for the next block?
Yeah. There's some kind of smart thing where there's multiple trees that are in progress at the same time.
And the orchestration of this process, is it also on the blockchain, or is that independent?
Sort of. So, like, is it certified? It's self-certified within the Snark. Is that what you mean, or?
No, my question is
Like
the
who is
information
doing
about
what?
Yes, yes.
which parts are
Yes,
computed
yes,
already
yes.
on the blockchain?
Yes, that information is in the blockchain. But this is actually worth mentioning. Who is actually producing these proofs? It doesn't have to be. It can be anyone. So there's actually a mechanism. Let me say there's kind of two kinds of nodes. Two kinds of nodes who are not just verifying. So two kinds of nodes who are computing. There's like staking nodes. People who are actually like proposing new blocks. And there's like snarking nodes, and they may be the same people. Basically, snarking nodes, they produce proofs which somehow have attached to them, I would like to receive this fee for this proof. And those are gossiped around the network. And then staking nodes can use those proofs when building their blocks to work on the tree that's in progress.
So in theory, they can screw up snarking node by just computing them themselves and including it because.
Yeah, if they want to. Yeah.
And so the only damage a staking node can do is waste some Snark computation resources, right?
They may not select this person's proofs. Yeah.
Oh, they can also do reworks, I guess, right?
Huh?
They can also do reworks, like they can fork out the chain, the staking nodes.
Oh yeah, we can talk about consensus. Is that
So
yeah.
one question, just to be clear.
Yeah.
So this is really like 30 seconds for a money transfer.
Yeah.
Transaction.
Yeah. But it would be similar. Yeah. There's techniques that you could do that would make it similar for more general kinds of computation too.
Like Turing complete.
Well, probably not. I mean, in some sense. So you can imagine doing like a Zexy style system.
Where you pretty much need to check in the type of program you want ahead of time.
Yeah.
And then
So
this verifies.
yeah. So like the off-chain computation would be more depending on the complexity of this program, but the on-chain computation the Snark work or whatever would still be small. Because you can just sort of recursively do recursive composition, basically. So like, if you have any computation, you make a Snark for it. And then in the way Zexy works, it's like all you're doing is certifying Snarks on chain. So you're not certifying the computation itself, but just a Snark that itself certifies the computation.
So like your transaction is a Snark, pretty much.
Yeah.
Like that's what hits the blockchain.
Yeah,
right?
the idea, right. Instead of a signature, you have a Snark. That's kind of the idea.
And Zexy only requires one trusted setup?
I guess it depends what you mean by one setup, but yeah.
Oh, only one one toxic waste left?
Yes, I mean if you did Zexy with like something like Sonic, for example. What?
But then why not use Sonics for
Right.
everything?
So I mean, I guess the problem with Sonic as it currently is it's slow. But I've heard that there ought to be similar systems which should be much faster, but they're not public yet. So. This is the only one that I know how to talk about.
But my question was about Zexy and Snarks because, so for example, in your case, right, you will do one trusted setup for your circuit that, I guess for like multiple circuits, right? You have a circuit for the payment, circuit for the
merging,
aggregation,
for the
yes.
wrapping, yeah. Oh, I didn't talk about the wrap. Whatever. I won't talk about that. It's cool. But
In Zexy, if I create a new, let's call it smart contract, do I do trusted setup per smart contract? Or do I do one smart, with Snarks, not with Sonics? Or I do one at the beginning?
So, sorry, Zexy with Snarks, not with Sonic.
With Snarks, yes.
Yeah, you'd have to do it once per
contract.
per program. Yeah,
I
per
see.
contract. Yeah.
Unfortunate.
Yeah, but you can use Sonic or soon,
Or Stark or anything, right?
Well, Sark is a little bit. Those other ones are more difficult to do.
Yeah, because you
proof
need to do
composition.
this. Yeah.
But yeah.
So you mentioned wrapping. That's for the whole block, pretty much.
Oh, yeah, well, sort of. So right. So there's this. Right. I mentioned like this is the general. We talked about the general technique of recursive composition, but there's if you try and do it in a naive way, all that we just described, you're in for a lot of pain, because that Snark verify function is going to be millions of constraints. Or actually probably even more. So how to not experience that pain, and that's what I was just talking about with the wrapping. But we can talk about that, or we can talk about consent. I don't know. It's up to you. How much time we got? All right. I don't know.
Yeah, we can talk about consensus a little bit more. I think that's
Okay. Yeah.
it's interesting how this all builds into a chain.
Oh wait, one more thing. While I'm on the video, I just want to say it. That we were talking about those Matter guys. We're also going to be doing a contest for improving the Snark prover, and in particular GPU implementations. So stay tuned for that. Follow us on Twitter. We'll tweet about it. Cool. Okay, so consensus. Yeah. What should we? How should we?
So can you actually give a high-level overview of Ouroboros?
Yeah, sure.
Because I think most of the people cannot really process that paper.
Right. Right. It's well known that if you mention this paper to someone, there's pretty much one thing they will say about it, which I won't say. Okay.
Oh yeah. First of all, nobody can spell it, so it's really hard to find it.
Yeah. Right. I think that's spelled correctly. So okay. So what's the basic idea of Ouroboros? So it's proof of stake. And it's I guess by IOHK people.
Which is Cardano, right?
Yeah. So, and it's they were the first paper is from like 2000. I want to say 2017 or something like that, 2016. But they've done a series of improvements. So it's a lot better than the original thing. But let me explain everything. Okay. So Ouroboros, how does it work? Basically, how it works is the following: you have time. Is it continuous? Is it discrete? I don't know. But you discretize time, and first you chop up time. Let's say, into slots. So slots. So this is this isn't that important, but you discretize time into slots.
How long is one slot?
So this is like the block time. Mm-hmm. So this is what you would want to be like 10 seconds-ish.
Do all the nodes assume to have, give or take, synchronous clocks?
Yes.
Like up to that precision?
Yes. Yeah.
Less than that.
Well, you'd want it to be more precise than that.
Yeah, they need to communicate right within that.
Okay. So, and then once you've broken up time into slots, you break it up further into what are called epochs. So
I just expand one slot.
So like it's some number. You break up this like this. Epochs are bigger than slots.
Okay.
So
That's just like how validated rotation and stuff.
it's something like that, except not exactly. But yeah, something like that. So these are epochs. This is epoch 0, epoch 1, and so on. And then the idea is basically at the beginning of each epoch, you have some randomness, okay, which somehow was given to you by nice people in the past, and you use that randomness to randomly sample, in some sense, who are going to be the winners in each of the slots in the subsequent epoch. Now, how you actually do that randomness, how you actually accumulate the randomness and how you actually select the winners, it depends based on, in the original Ouroboros it's one way, in Ouroboros Praus it's another way. And we use the techniques in Ouroboros Praus. They're much more conducive to to being snarked, and also I think just simpler and yeah. And then what Ouroboros Praus ends up giving you is somehow some kind of security. Okay, so like this gives you sort of the ability to sort of select or prefer a chain, to distinguish an attacker chain. Distinguish an attacker chain, assuming it did not fork too long ago from the chain that you know. And how long is too long? It's basically a fraction of an epoch. It's a fraction. It's a fraction of an epoch, or maybe it's a full epoch. I don't remember. Maybe it's fractions of one. I think it's a fraction of an epoch. Up to, forks, up to sort of recent forks. Okay, so that's no good. What that means is this is a good way to go so long as you're online frequently, right?
Or if a snapshot.
Or if you put on mybitcoinblockchainhash.com or whatever. Right. And so they wrote this other paper called Ouroboros Genesis, and this lets you distinguish, for long forks, actually arbitrarily long forks, but it's not really snarkable because it requires sort of looking, if you have a fork, it requires looking at the point where they forked and then making some judgment about that. And this is not a snarkable thing to say, oh, go look at an arbitrary point in the past. All you have is current state. So we have some modification. And I think Vanishri, who works with us, is writing a blog post about it, and so we'll write something up about this soon, which makes it snarkable. Okay, so which involves somehow computing some summary statistic that somehow approximates what you were doing by looking at the point where they forked. But yeah.
But in essence, it's the same.
It's a similar idea. Yeah.
So what happens within a slot?
Yes,
Like, you just
okay,
block
sure.
proposes?
Right. Yeah. How do you win? Right.
Yeah.
So here's how you win. And let me talk about Proust, and it's the same, exactly the same in Genesis. The only thing that changes in Genesis is the chain selection rule. So how do you win? So here's what you do. So at the beginning of an epoch, I have some randomness that was given to me by the very kind people from epoch n-1, called R. I think in the paper they call it a nonce. Okay, so it's some random bits that were somehow generated by these people in such a way that an adversary sort of can't mess with it. And say I'm here, and I'm like, hey, I wonder if I won epoch or slot number 3 or 2, because I'm counting from 0, 0, 1, 2. I wonder if I won slot number 2. And let's say, my public key, I have a public key U. My balance, my account balance is like, A or something, or B for balance, and the total amount of stake in the system is like T.
Oh, I'm assumed to stake my entire balance, or balance is specifically how much I staked.
You're staking your entire balance.
I see.
Yeah.
Awesome.
So, right. So, what you do is there's something called a VRF, which is like a verifiable random function, and it's actually really simple, and I can explain it. But basically, you somehow run your own private lottery, okay? And it's somehow associated to your public key. You have some personal random function which is somehow associated to your public key, and you evaluate it on basically the input.
The slot ID.
Yes, the slot ID, exactly. So like basically 2, or 1, 2, like epoch number, slot number, say. Oh, and then with the randomness.
So would a hash of a signature be a viable VRF?
That's basically it. That's almost exactly what you do. Yeah, pretty much. It can't be a hash of a signature because signatures have randomness in them, but you want to be able to grind. But that's almost exactly the idea. So what you do is basically you take the message and you raise it to your private key. You take the message, you interpret it as a group element somehow, and you raise it to your private key, and then you hash it. And then, yeah. So,
but then I don't know if I won, right? I just know if my number is big, I sort of.
And then you compare this number to some function of B and T. And you basically check. There's some threshold function, which say takes B and T as inputs and returns some
Pretty much
number.
says you should try or you shouldn't try.
Well, it will just be a real number, and you can compare.
You can compare with others, right? Like you're not gonna know immediately that you won. That sounds like magic, no? Because I don't know others. Others will have different VRFs, right? Which I do not know.
Is that what you're
Yeah. That's
I see multiple
that's what I'm
people
saying,
can
like,
win. Okay, yes.
Yeah.
So they all produce blocks pretty much. All of the
Everyone who
win
won produces a block.
produces
Yes.
a block with the transactions they have so far. They post it, and then everybody else pretty much does a chain rule.
Yep. And there's a parameter in the system which is like basically what percentage of the slots do you want to be full, and that also implicitly determines how often will there be multiple blocks per slot. And
But for example, so let's say like 4 people won here and they all produced blocks, right?
yeah.
Um,
Okay. So.
and let's say just me who won here.
Okay.
Nobody else won.
Okay.
Yeah, there is some algorithm which tells me which one to choose, but I can choose arbitrarily still, right? It's up to me.
That's true. Yeah.
Okay.
Yeah.
Like the chain length.
adversary, yeah, it's up to you.
Right, but then when I produced my block, right? So I said, I'm actually going to choose this one,
Okay.
even though this one was higher. I will just pretend I didn't see it.
Yeah, sure.
The next person will always prefer mine, right? Because mine is longer. Okay.
So yeah.
So we can attack up to.
There's some complicated analysis in Ouroboros. I encourage you to read it. It sort of it says if you don't have that much, if you don't have 50, it's not 50%. It's a little bit less actually. It's like 40 something percent. Then you can't do this often enough to win eventually.
And do people stake explicitly, or everyone who has any balance?
Is staking, yes.
It is staking.
And there's also delegation. So you can also you can say, actually, there's basically a bit in your account, or it's not a bit, actually, it's a public key. There's a field in your account which is like,
Cool.
who do I want to delegate to? By default, it's you. It's the same as the public key of the account. But if you want, I can say, hey, I don't really feel like staking. I'm going to set it to be your public key, and then.
Is there a slashing in Ouroboros?
No, actually. So that's I guess open.
So what if I propose 2 different blocks? Like I want to propose 2 different blocks and propagate them.
I forget exactly. I think if there's some explicit misbehavior, you just you ignore both of those persons' blocks or something like that, because they're adversarial blocks. Or I don't remember exactly.
It is.
I forget.
Oh, but because
I forget what
yeah.
we do, but I'm pretty sure if there's multiple blocks with the same proposer in one slot, you ignore all of the blocks.
I see.
I think that's.
And so that's effectively you're slashing because you're losing your reward, effectively.
I guess so. I don't know how to say it in those terms.
Yeah, I mean the problem is like with this kind of ignoring is that because you're getting more reward, especially if you're a bigger delegator, you're actually depriving them from reward long term, which means the people who delegate to them will lose the income and will see this other guy who has bigger income and they'll go to him. So you're actually like centralizing everything by censoring other people. And this is true about like proof of work as well, right? As a mining pool, you can actually start censoring other mining pools, and they're like if it's a small mining pool, their revenue drop is way higher than yours, and you can start like bringing people, hey, I have a better income. Anyway, I'm writing a blog post about that. That's why.
Yeah, that's cool. I never thought about that.
Yeah, it's interesting. I mean, so what's happening if pretty much like randomness happens, like randomness been generated from previous one, right? I mean, assuming it's like some randa with VDF or something that's not that cannot be
Yeah.
tangled with.
Yeah. So I forget exactly how it works out, but basically like there's the middle third of each epoch is like when the generation of this
I
randomness
see,
takes
okay.
place.
So like you actually know ahead of time who.
Yeah, it's
You know randomness kind of ahead of time.
Yes. It's frozen it's frozen here.
And so what happens is like, I mean, these guys are progressing, and then people like here they get kicked out for whatever reason, so they start building like a longer chain. That's pretty much where the well, like the validators here, right, that were that produce these blocks, they are not validators anymore.
Oh, they might be. Yeah.
No, but let's say like effectively describing long range
Yeah,
attack.
it's a like long range attack.
But
right?
that's what Genesis I guess is so.
The number of blocks that in each epoch the number of blocks that you would win is roughly proportional to well or at least this threshold function.
Yeah, because it's not selecting a subset, right? It's actually like a full. Everybody can participate.
But I guess another question is, so my VRF only depends on the randomness here, right? It does not depend on the random. It does not depend on the previous block, for example.
No.
Right.
So you know at the beginning of the epoch.
So immediately after the epoch has ended, no matter how much stake actually was in the system, right? I know exactly how much stake participated in this epoch, right? Like I can add up the stake of every. So this is the blockchain. Yeah. So I don't really need to wait for them to unstake. If I want to corrupt them, I can immediately pay them more than that, and immediately fork out, right?
Can you explain it again?
So let's say I'm an adversary.
Okay.
But I guess it sort of breaks if people are actually online and see the network. But like effectively, what I'm saying is that because I know everything. Like let's say I have a way to reach out to each of these people.
Okay.
Right, and so at any moment, like the moment this block was produced, I can already reach out to that person and say I will pay you a little more than your stake.
Oh, to like screw up your.
Not just take your reward because there is no slashing.
Because there's no slashing, right? I will just pay you a little more than your reward.
Yeah, and let's
For
post
your
this
private
block.
key. But they need to give the private key.
Well,
I just
no,
propose a
you're
block,
just
yes.
saying, yeah, you just say, hey, rewrite the block without this transaction, right? You had the transaction here, it's like, yeah, no transaction, awesome, and then you just pay everybody else, right? And in reality, you just needed to do like at the end of the epoch.
But they do not promise you more than one like part of the epoch. Like they're assuming that if something was like a fraction of an epoch in the past, then everybody already agreed on it. But here it seems like you can
But like
literally rewrite
this
the very
next guy
block.
can rewrite it. Pretty much the next guy, this guy decides which of these two chains to propose forward. Right?
Well, I
like
guess not
this guy, if he includes this, then like this chain is orphaned. I mean, I don't know if there's
All right,
more.
what happens? So let's say actually there's 40%, right, malicious. So there's a decent chance that I will have like let's say 2 first blocks. It's like 20%, right? So if I manage to corrupt some people here, which is very cheap to do, right? So let's say that the person staked like 50 Cardano tokens
doesn't matter. It's whatever the
Coda
reward
tokens.
for the block
Right.
is.
So reward could not be more than like a negligible percentage of that, right? Like if you think about 5% or like let's say even 50% annual yield,
Okay.
right? Your per block reward is going to be miserably small, right? So let's say you get like 0.1 of Cardano or Coda tokens. That means that for anything that is more than 0.1, like 0.2, for them it's actually very meaningful to rewrite the block. And because I already paid them 0.2, it's okay that they will not get any reward because it will be detected, right? But they will produce the block, and then I have these 2 slots. I will just approve this chain that I built by corrupting them. Does that make sense?
So there's no finality within an epoch, pretty much.
But I can build it more.
Yeah, basically. Yeah, I don't know. I mean, that's true. Yeah, I guess what you say is true. I'd have to think more about exactly what this attack is. But.
Cool. But is it something that Genesis sort of solves? Because you're saying Genesis actually has protection from any long-range attacks, right? So here the range is not even that long.
I think in their security arguments they assume
50% not corruptible.
something like that. Yeah.
I see. So it's I call it Algorand security. they have the same assumption.
Sure, something like that.
It might be reasonable, but
Yeah.
knowing people, I think it's.
Yeah, it's like post factum not corruptible, right? Which is like. economically decentralizable. All right.
Bought in. I don't know. Ideologically bought in. I don't know.
Yeah. All right, cool. And then, so pretty much in Coda, you run this, and then with some lag, you pretty much, while you're building this block, you have like a snark for this block, which kind of proves from Genesis till this.
But the light node,
Yeah.
the light node, it is not as easy as actually just downloading a snark and a Merkle path, right? Because
If they want to know something that happened recently, is that what you're talking about?
right, so
Yeah.
so effectively, I do need to download a few blocks, right?
If you want to know something that just happened, yeah, then you would have to. Yeah.
So,
But like, I want to know my balance, right? Oh, but I would know if I spent it. Sort of.
but you don't know if you received money.
But-
That's,
but yeah,
that's
so-
what usually
yeah,
you
okay.
want to check.
So effectively, what you're saying, like, let's say I want to check my balance, right? So if I know I wasn't spending anything, and I check something that was like 2 hours ago, I sort of know it's still
Yeah, yeah,
up to date.
Yeah, yeah, yeah.
Maybe someone sent me money in the last 2 hours. I will just know 2 hours later.
Yeah, and actually, there is sort of a they can also show you some parts of this buffer to also convince you that they send you money.
Right. So because there is a Merkle proof in on top of the buffer.
Yeah, the buffer is there's also like the hash of the buffer is also sort of in the state, and some information about that is actually certified.
I see. Cool. Okay. We covered everything.
I guess so, roughly.
Yeah. Awesome.
Awesome, yeah, that was super cool. All right, yeah, check out Coda, Twitter, website,
Yeah.
GitHub.
Competition.
Competition is
Competition.
upcoming.
Yeah.
Yeah. Leave comments and tweets. Thanks.
Okay, thanks, guys.
Cool.